Welcome along and welcome to the sixth and the final of these videos in a series called In Search of the Northern Lights. So I'm just going to find the PowerPoint that we're going to be having a look at today. Here we go. So what have we talked about so far? We've talked about some really great physics. We've talked about the Northern Lights, these beautiful bands of green and purple and red in the night sky. We've talked about what causes them, the ultimate source being the sun. We've talked about how particles get trapped by the Earth's magnetic field. We've talked about why we get these particular colours. We've talked about how we can work out the altitude of the Northern Lights. We've talked about some of the implications of space weather for technological systems. And what we're going to move on to talking about in this final session today is about going looking for the Northern Lights from a scientific point of view. So where would we go if we want to study the Northern Lights? Well, we go a very long way north indeed. On this map here, you can see Scotland down here. Here you see Norway. Round about here, you get the polar circle. Here's Nordkapp, the top of mainland Europe. And here's the island group of Svalbard, about halfway between the top of mainland Europe and the pole. Of course, we don't actually have to go that far. The Aurora Oval, the place where the Northern Lights are most common, is actually down here in northern Scandinavia. And there's all sorts of observing stations around there. But the one we're going to focus on here today is on the island group of Svalbard. Svalbard includes the most northerly permanently inhabited settlements in the world. It's an incredibly beautiful island group. I was lucky enough to take this photo from a plane flying up towards Longyearbyen, the main settlement on Svalbard. You can see this lovely big glacier here coming down and going into the sea. You can see tributary glaciers around here, and you can see this whole region of ice. That's a massive glacier feeding down around. You can see the mountains captured beautifully in the sunshine. It is an absolutely stunningly beautiful part of the world. It's home to 3,000 people and 3,000 polar bear. Now, the important parts of a polar bear from a point of view of a physicist are the claws, the teeth, and the stomach. And it's vital to avoid all three. So, the thing about polar bears, though, is so few polar bears have ever seen a person on Svalbard. There's 3,000 bears and there's 3,000 people. Where the people live tends to be concentrated in a few small areas. The polar bears roam all over the island group and all over the ice hunting seals. So you never know how they're going to react. Most bears react like this. They're not remotely interested in people at all. In fact, I knew some Arctic technology students on a field trip out to the east coast of Svalbard. And when they were out there, they set up camp for the evening. And they went out exploring, they came back to camp, and they found a polar bear stood in the middle of camp. So they tried to scare it away, and it wasn't remotely fussed. It was so unfazed by them and all their attempts to scare it away, it lay down and went to sleep. So they thought, well, we can't all split up in our tents and go out around this area and go to sleep with a polar bear in the middle of camp. So they stood there for 7 hours watching this bear sleep. It eventually got up, shook itself, walked off, and didn't even bat an eyelid. However, some other students who are down making temperature measurements in the ice at a place called Svea, well, what they found is they were putting all these sensors in the ice to see how the temperature of the ice might change as it went out across the fjords. And of course, you can get all sorts of uncertainties in those data. You can get uncertainties because of instrument limiting error. You can get uncertainties because of natural random variations. You can get uncertainties that based on variations between seasons. Sometimes the ice will melt quicker than others in different seasons. You can get uncertainties because a polar bear turns up and eats one of your sensors, which is exactly what happened to them. Then they had a little look around to see where else had this polar bear been. It had been checking out all their experimental equipment. They could see that from the polar bear tracks. It had been going round and round and round the cabin where they were going to sleep that evening. So it was taking a great interest in what they were up to. So they decided it might be wise to be a little bit careful on that trip. And of course, everything was absolutely fine. Now, if you have a look at this picture here, you can see an adult polar bear, which is not remotely interested in the photographer, and two much younger polar bears. And polar bears, especially males under the age of 2, are very inquisitive about their surroundings. And they're quite keen to find out what tastes good. So these two are eyeing up the photographer, thinking, I wonder what that photographer tastes like. Older polar bears, well, they tend to have classified the world into things they eat and everything else. So they tend to be not so much of a problem. You're so far north here on the island group of Svalbard. In winter, the sun never rises. This is a picture I was lucky enough to take in Longyearbyen in February 2002. This was taken at the stroke of midday. There's no difference in midday and midnight, 24-hour darkness. This here is Svalbard Butikken, the shop. It's the only shop for about 700 miles in any direction, and they advertise. I have never understood why they advertise. They could say things like, buy things or don't, see if we care. Don't want to shop here? You will when you get hungry. But yeah, it's a really wonderful place. In summer, the sun never sets. It just goes round and round the sky. It's the land of the midnight sun. I was lucky enough to take this photo myself on the stroke of midnight. And it's a phenomenally beautiful place in which to work. This photo is taken from the control room of the Aurora Station, where we make measurements of space weather phenomena and the Northern Lights. And you can see the line of jagged mountains on the horizon. Those are about 60 kilometers away, and it's crystal clear. You can see the beautiful sharp relief of the mountains. You can see a glacier here as well. It's a really wonderful place to work. This is the Aurora Station, where you have a whole load of different instruments observing the Northern Lights. You've got things like the meridian scanning photometers that we looked at in a previous session. You've got magnetometers that look at disturbances of the Earth's magnetic field. And out here on this platform is an experiment I was lucky enough to be involved in, called ionospheric radiotomography. So here we've got a receiver, and what this receiver does is it looks at signals coming from satellites that do things like GPS. And these signals, they tell us about the structure of the upper atmosphere. They can tell us about things like our plasma structures there. As I said, I was lucky enough to be involved in this experiment. We got some great results out of it. I played a fairly minor part in that, but it's always wonderful to be even a small cog in a very big, useful result. I was involved in deploying and maintaining some of this equipment. And if we look in, and that was great fun. You can get as far as Longyearbyen, the main settlement on Svalbard, on a 737. But then, in order to reach some of the more remote locations, such as New Orleans, where we had some of this equipment deployed as well, you'd take a little aeroplane like this. And that's great fun. You get on this, and the pilot says, use it here, use it here, use it here, to balance the weight on the aircraft. And this is the sort of equipment we were installing, not just the receiver that we saw outside, but other things as well. So what you can see here is we've got these things here called Nav Guides. And what these Nav Guides do is they take the signal from the receiver that we saw just now, and they take a signal from GPS to get a precise timing information. And they combine that and they send it to this thing here called an itomo box. This looks like a computer, but it's not really. This is to process the signal. The signal comes in at such high frequency, we need to do something with it to extract useful information and to put it into a form that a computer can deal with. And there is the computer, which is then logging the data and sending it back to the UK every night. Now, if you're arranging an experiment in a lab and it doesn't work, you can go back and hit it the next day and make it work. That doesn't work when deploying equipment in the Arctic. There's only a limited season when it was suitable to do this, and that was early autumn, because you need to have light, and you need to have a sufficiently small amount of snow, which means you can set up things outside. Yeah, so it's a limited window, and it meant this all had to be done on a single trip every year. So it meant everything had to be set up and had to work. Now, what we do as physicists is we take equipment and we push it to the limits of what it can do. And then having pushed it to the limits, we see what else it can do as well. And that means that we really are taking things to the limit all the time. Also, we need specialist equipment. So if you think about, I don't know, something like Microsoft Word, who knows how many copies of that there are around the world? Hundreds of millions, billions, who knows? It's a colossal number. When you think about things like these itomo boxes and these nav guides, there were 8 of them built. 4 for use, 4 for testing and repairs. And so that means not all the bugs were ironed out. Some nav guides would work with some itomo boxes, not others. Some itomo boxes would talk to some computers and not others. So we had to rigorously test things back in the UK. And once we tested these, we saw, well, which ones were working with which pieces of equipment. And this meant we had to keep very careful documentation. We had to keep notes of all the different serial numbers, see what worked together in combination, and test these over a period of time. Ideally a couple of weeks to make sure it really was working. So when we deployed equipment, we could put it together, test it's working as it did in the UK, and then we'd be confident that everything was going to be all right. Here is one of the receivers we deployed at New Orleans. So this is the most northerly, permanently inhabited settlement in the world. It is almost exclusively used by scientists to make scientific measurements about things like space weather, but also things like the biology and the ecology of the Arctic. Now you can see there's a rather heavy-duty cable here. We needed these heavy-duty cables because we needed to be able to deploy this equipment in places where it could get run over by things like snow scooters. It's not going to get run over here, obviously, but we're using the same equipment everywhere. That proved a bit of a challenge to try and get it wired up through the building because heavy-duty cables don't bend terribly easily. This took us about half a day. And then here is the equipment all happily working. And then, of course, we needed to make sure it was going to continue to work. So we needed to pop in every couple of hours for a few days to make sure it really was doing what it should be doing. And of course, it's a phenomenally beautiful place to work. We also use data from the Icecap radars. And this is what the Icecap radars look like, high above Advent Fjorden here. The Icecap radars are big. It stands for European Incoherent Scatter. This dish here is 42 meters across, 42 meters in diameter. It is glued to the floor. It points in the same direction all the time. This one over here, the smaller dish, 32 meters in diameter, can be moved to point around the sky. And this looks at the plasma in the upper atmosphere. This can be caused by space weather phenomena or by sunlight. And it can be structured by the variability of space weather. And so we can investigate these wonderful phenomena. This is a little image here of some people in it, just to show you how big these dishes are. I was lucky enough to stand up inside this disc, obviously when it was turned off, and you see these walls of white towering up towards the sky in all directions. It's a very bizarre experience. And I say it's a phenomenally beautiful place to work. This is a photo taken of the Icecap radar dishes from the control room at the Northern Lights Station. And here's just a lovely image, New Orleans, again from where we were working. And you can see the fjords, you can see the glaciers, you can see the mountains. As physicists, we're very, very lucky to be able to live and work in some of these places. So why am I showing you all this? Why am I showing you my amazing snaps from a work trip? Well, one of the things I did as an undergraduate student is I had the opportunity to go up to Svalbard and spend a bit of time there towards the end of my degree. And there's all sorts of opportunities that different universities provide for their undergraduate physics students. And what we're going to look at next week on this YouTube channel is I'm going to show you about some of the particular opportunities that are available within a physics degree. This is not a hard sell for Nottingham-Trent University. It will not be a hard sell for a physics degree. It is simply to tell you about the sorts of opportunities that are out there and the sorts of things you might want to investigate. So in the fullness of time, you can make an informed decision about whether this sort of thing is right for you. Okay, so that's where we're going to finish this video today. Thank you very much for your attention and I hope to chat to you next week.